Okay, well, welcome everybody. I see another question in the chat. When will the wiki be posted? I should get it up tonight. I'm anticipating 3 a.m. We'll see what time it goes up. So don't worry if you go, I can't get to the wiki. I haven't set it up yet. Everybody will get their own page. I have some slides on that, so I'll be giving you a little more information on that in this lecture. There's a question, is the wiki the same thing as the team charter? No. So you'll see that in this lecture. Yeah, I see someone saying, I am one of you. Yeah, I've gradually learned through hard experience not to leave things that I don't know how to do to the last minute. The wiki I know how to do, so I'm leaving it to the last minute, but it'll work out. Anything I haven't done before, I try to get done a
Vaughn,
little
your
farther in advance.
audio is going in and out. You're cutting out right now.
Oh, sorry about that. Let's see. Is that better at all?
Yeah, I've got you now.
Okay, I was probably too far away from the microphone. Okay, let me adjust this video display too. Okay, I need to share my screen and let's get going. Okay. Okay, so we're going to talk some more. First part of this lecture is going to be more about Milestone 1. So some more tips on how to do it, a little more information. And just organize all these Zoom windows. Okay, so as I mentioned at the end of last lecture, your specification is in m1.h. So the header file says, here are all the functions you have to write, and you can't change this header file. That's why it's read-only. Otherwise, you can just delete all these prototypes and say, there, I changed the specification. Not allowed to do that. So what's in here? So here's a particular function. So find street segments of intersection that we were talking about last class. And it has this speed requirement high marked on it. And in the header file, okay, so it basically tells you, what do you have to do? This particular function has to return the street segments connected to a certain intersection. So it's getting a little piece of the graph showing that you can use this API. And we say it has to be fast. Okay, speed requirement is high. And in the header file, there's this big comment that says, what are these speed requirements? So high means, you're probably going to have to create some data structures of your own that allow you to rapidly return the right data instead of just making calls to the Streets database API. So it's probably going to involve you doing something a little more clever, creating your own data structures. Moderate means we're going to speed test it, but we think that you should be able to pass our speed test just by directly calling Streets database API. You probably don't have to load up any data in advance. You're allowed to if you want, but you shouldn't have to. And none, there are some functions that we don't care about their speed, and we don't have any speed tests at all. Okay, so that particular function says need to make it fast. But what does that mean? So, well, the other part of our specification is the tests. So ECE 297 exercise runs the public unit tests, and that is a part of the specification because it's test-driven development, as I talked about yesterday. So all the functions are tested for correct results, and the tests that check just for functionality or correctness all have the word func in them. So this is a piece of the output from ECE 297 exercise, and you can see there are a couple functions here that have the word func in them. So they're just testing. This did 5 different tests, and all of them passed. So it comes out green, and they weren't timed. This was just about getting the right answer. And the same for the second one. And then I've got 3 more tests down here that have perf in their name. So those ones are testing, was your code fast enough? So for the performance test, how do we set this performance target? You're writing a low-level API. So you're writing a bunch of basic utility functions that many of which will be helpful to you in the rest of the project. So we can't set a performance target based on some kind of end user behavior, like how fast humans want programs to be or things like that. It doesn't really make sense for these low-level APIs. So what we do instead is we use an STL-like approach. What STL does for each of its data structures, like vector, map, unordered map, is they basically specify that the big O notation, the computational complexity, is going to have to be the lowest that it can be so that the function is fast. Okay, so for the functions where we say the performance target is high, you're basically going to have to use the best big O implementation. Maybe you'll pass it with something that's not quite that good, but the way we set up our tests are we're checking, are you close to the speed of something that uses the best big O that we know of? Okay, how are you going to do this? So I'm going to show you this in a couple slides, but there's going to be, you're going to have this load map function that allows you, that we're always going to call before we call any of the other functions that you wrote in M1. So load map is your chance to set up data structures and allow you to make the rest of the calls we make faster. And load map can be pretty slow. So it can be order n, where n is the number of intersections or street segments, basically the size of the city, or a bit higher. And you really can't do any better than that. We're giving you all this data on the city. It's order n data. You can't avoid reading it. So your load map's going to be order n no matter what. Even loading the streets database API, which you have to do, that's an order n operation. And we give you actually several seconds, which is a long time. So load map can be pretty slow. For these performance requirement high functions, yeah, as I said, you have to use the data structure or algorithm that leads to either the best big O or close enough that you pass our test anyway. But if you can think of what would be the best big O algorithm and data structure you could use, that's what you would want to use. So what is ECE 297 exercise test? So all of our implementations of these performance requirement high functions use the best big O. Okay, so if it's possible to make an order one solution, we make an order one solution. If it's possible to make an order log n solution, we make an order log n solution. And then we don't want to worry about sort of micro optimizing it, like trying to tweak the little details of the code. So we allow you to be 3 times slower than that. And we haven't micro-tuned ours. You know, we wrote something with the best big O and reasonable coding, and we allow you to be up to 3 times slower than that. So you don't need to micro-optimize this, okay? So I see some other questions here. Are these public? Yes. So ECE 297 are the public tests. We also, as I said, run some private tests. Those private tests are no harder. The performance requirements are set exactly the same way. So if you pass the performance requirements on ECE 297 exercise, you will pass them on the private tests as well. Can you do order n squared? So, okay, so I told you that you could use order n in load map. Well, what about order n squared? Maybe you can pre-compute even more stuff. No, order n squared is going to be huge, okay? So for cities where n is 200,000, for some of the biggest cities like Tokyo, it's like 1 million intersections and street segments. Order n squared is an awful lot slower than order n, and your program will take minutes to hours to load. So you're going to fail if you do that. Well, you'll fail that test because we do have a performance test on load map. It's just pretty generous, but it's not infinitely generous. Let's see. Okay, I see a bunch of other detailed questions. So, but maybe I'll just keep going, and at the end of the lecture, if there are still questions, you can ask me about those. Okay, so what are these unit tests that ECE 297 exercise basically is an executable program that runs unit tests. So it's connecting these tests to your libstreetmap library. That's why when you go into your project that's created for you for Milestone 1, you're going to see that you should write basically all your code in the libstreetmap directory, because that's going to build into a library called libstreetmap, which is what we're going to test with ECE 297 exercise. You should not be writing much or any code for Milestone 1 in the main subdirectory, okay? This is all about building that library that you're going to use. Okay, so what do our unit tests look like? They all look like this. So every test run by exercise has the same structure. It calls load map with some map, often Toronto, but not always. And load map is one of the functions that you write. So we're going to pass it a string, which is the name of the data file that you should load to get the streets database API ready, and then do anything else you want. Load any data structures you like, and then eventually you return from load map. After we return, this unit test is going to call some of your other API functions. So this particular one is about testing some of your intersection related functions. So for example, it's going to call find closest intersection, okay? And it's going to pass in a lat long position. So we've got some variable my position that we've set. We say, what's the closest intersection? We capture the result in this inter ID, and we already know the answer. For the my position we passed you, we know that the intersection ID that is closest to it in Toronto is this, 22,333. If you did not return that value, you failed the test. We're going to record that. And then we do a lot more tests like this. So the report that you get from ECU 297 exercise basically will run maybe 100 or 200 separate calls of this function. And if all of them work, we'll say you passed the test for find closest intersection. And if any of them fail, we'll say you failed. You failed 2 out of 200 tests. And these tests are public. You can go look at the code, and the unit test quick start guide shows you how to do that. And in a tutorial in a week or two, we'll demonstrate it. But you can go look at the code so you can run it in the debugger and say, okay, for those 2 that failed, let's see exactly what happened. So you can figure it out. When we're done with these maybe 200 tests of this function, we're going to call close map. So close map should clean everything up. So in load map, you loaded some data structures, you loaded the streets database API. In close map, you should do the opposite. Whatever memory you created, you should get rid of, so you don't have any memory leaks. Okay, let's see. So let's look at this load map. You can load anything you want here. So what should you do in load map? You've got 2 basic approaches. One is that load map does the minimum. Okay, so it only loads the data needed by the streets database API. Okay, so that's streets database API. What is going on here? So okay, so you have to at least load its data, or you can't do anything. If you do that, if that's the only thing you do in load map, then every one of the M1 API functions you have to write, you're going to write it so that all it does is it calls this lower level streets database API however many times it needs to in order to construct the answer, and then it's going to return the answer. Okay, so the advantage of this is that's stateless. You're not actually doing much in load map. You're not loading data structures. You're just going to make queries to our API. That tends to be easier to debug because your code is simpler. But the downside is that it's going to be too slow for some calls. There are some questions we ask you where you're going to have to call streets database API many times in order to construct the answer, and it's going to be slow. So you're not going to pass all the speed tests doing this. Okay, the other option is load map creates some new data structures. And now you can use them for API calls that need them for speed. So you can basically pre-compute things. And you can pre-compute, you've got enough time in load map that you can pre-compute a lot of different things. I saw a question about space requirements, actually. I forgot to answer it. As long as you don't run out of memory on the UG machines, which have 16 gigs of memory, and remember, we'll always run you on an unloaded machine, so you can basically use all of that 16 gigs minus whatever the operating system used. We don't care. So if you run out of memory and you crash, that's bad. If you do not run out of memory and you don't crash, that's fine. 16 gigs is quite a bit. These city maps are pretty large, but you shouldn't have a problem unless you do strange things. Well, you will not have a problem unless you do strange things running out of memory. Let's see. Okay, I think I see a question from Grace of, this is for find, let me go back for a second here. I think you're asking, what if this my position is at a midpoint? So I think by that you mean we have 2 intersections here and here, and we ask you for this position, X, a certain lat long, what's the closest intersection? You're saying, well, what if it's equally distant? What are you supposed to return? We basically, in the unit test, we're pretty careful, okay? But depending on the test, we've done one of 2 things. We'll either never ask you this question. We basically check, is this too close to having 2 correct answers? And therefore, when we create the unit test, we eliminate it. We will not ask that question, or we'll accept both, okay? So, if we make a mistake, point it out. But we've been pretty careful that whenever there's a tie or you could be affected by round off error, we'll accept any valid answer for that. which is the way you should write unit tests, right? The unit tests are the specification. The specification shouldn't be specifying what you do for round off. Anyways, that's a good question. So you can create some new data structures in load map where you need them. Use those new data structures for speed. As I showed you in M1.h, there are some functions that can be pretty slow. So for those ones, there's probably, you're allowed to create new data structures you want, but there's probably no real purpose to doing it. You can just call the lower level API, do it with the simplest code you can, and it's fast enough. So you're going to wind up with a mix. Okay, but you will have to load some data structures in order to pass the speed tests. It's not possible to pass them all without doing that. Let's see, I see some detailed questions, which maybe I'll talk about after we get through all the slides. Okay, so my suggestion is to code this in the simplest way possible, usually option 1. So option 1 is the stateless one, just call our lower level API, answer the question, pass functionality. You're going to fail some performance tests, but that's okay. For the cases where it's not fast enough, then recode it using approach 2. The code for approach 2 will share, you'll reuse some of this code, okay? So it's not going to be a throwaway code, even when you have to load some data structure in order to make it fast enough. The advantage of this is it's always really dangerous in a program when things aren't working. You want to get something working as fast as you can and then improve it. And coding in the simplest way gets you passing functionality sooner, and then you can work on performance. So that's my suggestion. Load map is also speed tested, so you can't make it infinitely slow. Order n squared is going to be too slow, but this time limit is pretty loose. So it's several seconds, which even for this relatively large amount of data, you can do a lot in several seconds. Okay, so let's see. What does stateless mean for option 1? Stateless just means it's a complicated way of saying you didn't load any data structures. All right, you had to load the Streets database API, but after that, every function we call, you just call the Streets database API, perhaps a whole bunch of times. You construct the answer and you return it. So you're not actually retaining any data or any state between calls to the functions you have to write. It tends to be a bit easier to debug, but as I said, for some functions, it's going to be too slow. And let's see. I see a question from Isidore. Can you kind of hack the tests by saying, can I kind of try to say, by being faster on one test does not help you pass another test. Like, you don't get to bank time. So when we test a certain function, we're going to call that function maybe a few hundred times. We're going to see how long it takes you to answer all those questions, and we're going to see if it was fast enough. And then we're going to have a different performance test that calls some other function a few hundred times and checks if that was fast enough. So you can't bank time. You can't say this function was extra fast, so therefore can I use that for this other function? No, you'll pass one performance test and fail the other one. Does load map return anything? Yes, load map returns a Boolean which says whether or not the load was successful. So if anything goes wrong with the load, which in Milestone 1 it normally won't, well, we may have a test where we pass you a bad name. If we pass you a bad map that doesn't make any sense, and the loading Streets database fails, then you should return a failure code. And that's specified in M1.h. So read the comments in M1.h carefully. If we go to the effort of specifying what you should do in the following state, we are going to test it. Okay, so read the comments carefully. This question, can you get partial marks? Yes. I mean, we look at how many tests you passed, and we don't expect everybody to get everything perfect. This is not a lab. We make some of the tests are not very hard, some are harder. And the idea is that it shouldn't be trivial to get 100%. But not getting everything right doesn't mean you get 0%. You obviously get partial marks. Okay, so let me give an example of how can we make our code faster for this API. So this is one of the functions that you actually have to write. It's called find intersection of street. And it takes as input a street ID. So remember, this is just an integer, but we give it another name of a street index so you remember what kind of integer it is or what that integer represents. So we're going to pass in the ID of a street, and you have to return a vector of intersection indexes. So the IDs of all the intersections, there could be many, that are on that street. So this is Yonge Street, and Yonge Street has a lot of intersections on it. So we should return a vector with an integer for every one of these little dots, right? So that might be intersection 1,000. This might be intersection 3,300. And those should both be in the vector along with a bunch more intersections. Okay, how can we do this? Well, we need to use Streets Database API. That's your link to this OpenStreetMap data. You can ask a street segment about its from and to intersections. Okay, so we have, let's see if I highlighted this. So Young Street's actually made out of a bunch of different street segments. And Streets Database API, if you go look through this API, you'll find there is no function that will just return the intersections of a street. So you can't just call one function and you're done. It's going to be a bit harder than that. So you look, okay, well, what else is in there? Maybe there's something in there that can help me. Well, you can ask about street segments, and you can ask a street segment, what's your from intersection? So one end. What's your to intersection? So the other end. And a street segment also knows what street it is part of. Okay, so street segments know a lot. Streets, however, cannot directly answer questions about intersections. So we're going to have to construct this answer by making a bunch of calls to this Streets Database API and gradually building up, this answer, this vector. Okay, so I'm going to try to put you in breakout rooms. See if I can do this successfully now. And what I want you to do is, so you can see these slides. If you lose this view when you're put in the breakout room, this is on the course website, Quarkus, so you can grab this information. And basically what I want you to do is just discuss in your breakout room, how would you attack this? You're going to use these street database APIs. So what ones are you going to need? Well, there's a call to get the number of street segments. Okay, that could be useful. For any given street segment, so a certain street segment ID, you can ask for some info about it. What's in that info? In that info, you have the intersection index, two of them, from and to, and you have the street index. So you have the ID of the street that this street segment is part of. Okay, so given all that information, that's it. That is enough. These two API calls and this one data structure are enough to write this function. So I'm going to put you in breakout rooms, take a few minutes, discuss how would you do this, and then I'll get you to type it in the chat or verbally tell me how you attacked it in a few minutes when we come back. Okay, so let me make these breakout rooms now. Okay. So we will meet back here in a few minutes.
Hamilton.
Vaughn, it looks like you're muted.
Thanks. I joined one of the breakout rooms, so I guess that mutes me. So thanks, Ken. Okay, so who wants to take a shot at how we do this? And I can see some people in the chat are already taking a crack at this. Let's see. Yeah, okay. Walk me through kind of the straightforward solution. So how do we do this without doing anything in load map? Let's start with that. It looks like we got a couple people who are already thinking about how can we speed this up with load map, and there are ways to do it, but let's not go there yet. What do we do if we didn't have any load map? We didn't have the ability to create any data structures. Okay, so I see make a vector and then iterate over all of the nodes. What does node mean? Node's a little vague. What are we going to iterate over? So we can make an empty vector of the intersections. And then we're going to use get num street segments to see how many street segments there are. Going to loop through all of them. And we're going to use pushback to put, we don't want to put the segment in the vector. I see someone saying put the segment in. Yeah, we want to go through all of the street segments. So that's going to be a loop. From 0 to num street segments minus 1. We want to check if that street segment is part of the correct street. And the street segment does know what street it's part of. So we can check that. Oops. And then if it is, we're going to get its from and to intersection and push those into the vector. And we're going to keep doing that. Okay, so let's look at that code first, and then I'm going to ask you what the computational complexity is. All right, so basically, this is just writing down what you just described. So that's exactly right. We're going to create a vector. That's going to be what we're going to return. And we're calling the default constructor here, or it's being default constructed. So it's initialized to empty. An empty vector called intervec, vector of intersections. That's what I'm trying to compute. I am going to loop over the street segments. So I use a nice variable name. Stir seg. So to me, that means street segment. And I want to do that over all of them. Okay, so while it's less than get num street segments, I'm going to keep incrementing my counter. For every one of those street segments, I'm going to call get street segment info. And then if the street segment info street ID, so if this particular street segment is part of Yonge Street, that's the one I'm checking for, then I'm going to go and add the from and to intersections to intervec. I'm going to use vector.pushback. We know vectors have a nice, fast way to grow. I'm going to call it. And when I'm done, I'm going to return this vector. Okay, so this will work. What is the computational complexity of this? Because this particular function in m1.h says its performance requirement is high. Okay, so this is functional, but is it fast enough? Yeah, so people are saying order n, and yet it is order n. So all of the code in here, like get street segment info, an equality test, etc., all of this code is order 1. But I got this big loop around it. Okay, I'm going through all of the street segments, order n. So that seems a bit high. Let's think performance requirement high, which is what this function is, means we're supposed to use the best O we can. Okay, so we've achieved order n. Is that the fastest possible? Well, let's think about what we actually have to return. Yonge Street has a whole bunch of intersections in it. The best possible implementation would just return however many intersections that is. And that is, let's say call that K. Okay, so K is the number of intersections on the street. And for a long street like Yonge Street, that might be quite a few. Yonge Street might have a couple hundred of intersections, but it's definitely not the 200,000 or so intersections in a city like Toronto. So this is a much smaller value than the order n, where n is the whole size of the city. So In theory, we could answer this question much faster because the amount of data we need to return is much smaller. How can we do it? You cannot do it by directly calling Streets Database API, because you'll find that the Streets Database API has a moderate number of functions, but not that many. So you can read the whole header file and you'll gradually learn all of the functions. And there is no function that will just let you get these intersections from a street efficiently. What you just did is the best you can do, unless you store data in load map to make it faster. Okay, so to pass the performance, let's see, next question, does get number of street segments give you the number on that specific street? No, if we go back and look at get number of street segments, it doesn't take any parameters. It is the number of street segments in the whole city. There is no function that it says get num street segments for a street on purpose. Okay, so but that's fine. Okay, we have load map. That's where we can make this faster. So remember I told you that the unit tests are going to call load map before they call any of your other functions. So we call load map, you write this code, you do whatever you want there, and then we're going to call, I'm changed now to find closest intersection, but it's the same idea for all of your functions. Okay, so, and then we're going to close map at the end. We run valgrind on a sequence of load map, use it with some API calls, and then close map. What that means is make sure your close map cleans up your memory. That won't affect passing most of the tests because they don't really care if you leave memory lying around, but it will make you fail valgrind if you just leak memory. So you should close the map. And we might also do more than one map in sequence. So if you don't properly close a map, then the next load might fail. So make sure that you actually properly clean up after yourself. Okay. Before I go now into how to speed up this API, let's talk a little more about memory checking. So we're running valgrind on your program. It's going to check for memory leaks. It's going to check for memory faults, accessing memory that's outside the bounds of a vector array and so on. But valgrind slows down your program, slows it down by about 10 times. So that could be painful if we do it on a big test case. So whenever you're making tests, which we've done for you in EC 297 exercise, but you'll do in your own programs, later in your career, you want to balance between being fast and being thorough. So this valgrind test is going to be pretty slow. We'll get most of the value of this test. We run it on a small test case because we'll probably have the same memory faults on a small test case as a big one. So that's what we do. We scale down the test case for valgrind so it doesn't take too long. So you're going to find this one map that we're running on. It's the smallest one you have. It's St. Helena. This is the street map for St. Helena. So it's an island and it's only got a few streets. So even with this slowdown, it runs pretty fast. Anybody know what the claim to fame of St. Helena is? It's a small island in the middle of the South Atlantic Ocean. What is it famous for? Yeah, so it was where Napoleon was. So it's way out in the middle of the South Atlantic. It's where Napoleon was banished after his second attempt. They've first banished him on, I think it was Elba in the Mediterranean after he lost a war. And he escaped from there, came back, fought another war. So they decided, okay, we're going to banish you there. And that's about as far away as we can get. So when you're doing St. Helena, you can, if you're debugging those valgrind errors and they're kind of getting you down, you can at least say that you weren't banished to the middle of the South Atlantic. So I see some political questions. Why not just execute him? It's actually interesting that he didn't, given the fact that he actually came back from exile and fought another war that none of his many enemies actually did execute them. They still banished him. I don't know the answer to that, actually. It is an interesting question. So that was about memory checking. But now so whatever load map creates, close map should destroy, undo everything. We still have a problem here of load map is given the name of some map. So it can load all the data in. But there's no connection between load map and the next call. So this is find closest intersection. So find closest intersection needs to access some data structures that load map created. How do we get that data to it? So what do you think? What do we do? how are we going to move data from load map to the functions that might need to access those extra data structures we created? Because you can't change m1.h. So that's the API. You can't go and put a bunch more parameters in there that are going to get passed and forth back between them. Yeah, so I see you can use global variables. And that's right. You have to use at least one global variable in order to do this. I see somebody saying static variables. Static variables are very similar to global variables. So yeah, you can do things like that, but they're all kind of different versions of global variables. Okay, so aren't global variables bad? You've probably been taught that in your prior coding courses, and it's true, right? Global variables definitely can be bad if you overuse them. So if you basically go, I don't really like typing, I don't want to pass any arguments, I'm just going to use global variables for everything, your program is extremely hard to understand, right? All functions are basically can access all state in the program. That's chaos. So don't do that. But almost all programs do have some global variables or something very similar. There are a few ways you can kind of hide global variables a bit, but they're essentially still global variables. So for example, whenever you've done output so far, you've been using standard cout. Standard cout is a global variable. So there are a few global variables in pretty much every program. You want to limit their number. So you want to group for this project, a good technique would be to group related data into classes. So you might make a class called street graph or anything you want, so that instead of having a whole bunch of global variables, you actually have one global variable that is a class with a bunch of submembers. So it organizes the data and it avoids a lot of namespace pollution. You only have one name to avoid because it's in your local variable names because you got one global variable. And it kind of that class has organized everything. This is all the data that I create in load map to make my API fast. So if I make some class called street graph and I make an object of type street graph, my load map and close map basically create it, and my find closest intersection can now access it. And we can use that to speed up any API call we want by loading appropriate data in load map. I see a question, what do we have inside this global class? That's up to you, right? So that is the part of the point of Milestone 1. You've been taught STL, so you've been taught how to create various data structures quickly. STL lets you just choose the data structure and then code it. You're learning the streets database API, so you're learning how to query the maps. You now have to think for the various functions we've given you in m1.h, well, what data would be convenient? And you can load that and use it to answer these API calls. Okay, so grouping things into one class will help you keep your program cleaner for this global state. You also want to be disciplined in your use of it. So if you have undisciplined use of globals, meaning everybody reads and writes them, they're changed all over the program, it's very hard to figure out what a function does. Not only does it have inputs and outputs that you can see from the parameters of the function and its return value, it also might just change this global variable, which is not visible in the function prototype. So a good way to do this is in all of your m1.h API functions except load map and close map, you only read the global variables. So those global variables are there to help you answer questions faster. Just read them. And you only change the global variables in load map and close map. Okay, so that's it for kind of recommendations of how to attack m1.h. And ask questions on Piazza. Parts of the API confuse you, but you now have to kind of just jump into it and start read the document and start trying to implement this API. We'll be continuing to go over how to attack a sample function in m1.h in next week's tutorial, and we'll also get into how to debug with the unit tests we've given you effectively. So I really recommend you go to the next tutorial as well. One of the functions in m1.h asks you to compute the area of features. So remember, features are these polygons. So the ones that are interesting for this are the closed polygons, maybe this pond in High Park. And one of the API calls asks you to compute its area. Okay, so that might seem tricky for an arbitrary polygon. Does anybody have an idea of how you might attack this? And all of the polygons that will give you for features are what are called simple polygons. It means they have no holes. Okay, so this pond does not have a hole in the middle. Okay, so that little circle will not exist. So triangles, yeah, you basically kind of break it up. So that's correct. Is it actually a formula that computes the area of any convex polygon? Yeah. So there is a well-known procedure to do this. Let's see. So let me walk you through it, because instead of just using the formula, it's actually a kind of elegant. How can you do this quickly? So let's say this is the first point, point 0, and let's say this is the next point. When you ask Street's database about these features, it will tell you the points that make up the boundary of the feature in order. So maybe this is the first one, this is the second one. We can basically get the x and y. So we can take y2 minus y1, and that's the height of this. And to compute the area to the y-axis, we could take that and multiply it by the average x. The average x is just x2 plus x1 divided by 2. All right, and they just computed this little piece of area. Okay, so it's like an integral. If we do that for the next point, right, so we're looping through this, we do that for the next point, you're going to compute this. Do it for the next point, whoops, let me go back there. Do it for the next point, we're going to compute this piece. Next point, we compute that piece. Okay, so we're up here. We're not done the polygon yet, and we've kind of overcounted its area. But let me switch colors here now. Okay, so we still aren't done. So we're going from that point to this point. And if we've written a loop over all the points, that's what's going to happen. At this point, that was y2, y3, y4, y5. That is y6 minus y5. Okay, so that's the distance we've gone down here. And we take that and we multiply that by x6 plus x5. So the average distance, x6 plus x5 divided by 2. This y6 minus y5, we're actually now going down. So this is negative. Okay, so what that's going to do is it's going to compute a negative area, which is this yellow. So it's actually going to subtract off that overcounted area. And we keep going till we get to the end of the polygon. We're going to actually subtract off this overcounted area. So if you take this procedure, yeah, sorry about the yellow being hard to see. I'll change it next time. If you follow this procedure, you'll get the area of an arbitrary polygon. So it seems like it would be hard to compute that area, but it's not very difficult. Where do you get the coordinates from? You get the coordinates from Street's database API. Let me change this back to red. There's a function in there to ask point by point, tell me the next point, tell me the next point, okay? It's actually someone's asking about a horseshoe, and it will work for a horseshoe as well. So walk through with a horseshoe and it'll work. So, all right, so we've got not long, but let's talk a little bit about team formation. I think you saw this in APS 111, 112. So, but it bears a very quick repeating. So there are 4 stages of team formation that, Bruce Tuckman documented. Forming, where you're picking your team, you're getting to know each other, so you don't really know how you're going to work together at all. Storming, okay, you're trying to work together, but you don't really know how to work together very well, so it can be contentious, trying to figure out who does what. Norming, where you're gradually starting to refine your roles, write down some rules, or fall into some routine. And performing, which not all teams ever get to. Okay, so performing is everybody knows what they should do, but you openly discuss problems, you improve. There tends to be high trust. I guess the reason I'm telling you this is because I've seen this. I've formed many teams over my career, some small, some quite big. And it's comforting to know that you typically go through this procedure. If you already know your teammates, then you might jump straight in here, right? You already know them and you know how to work together pretty well. But more commonly, you don't know your teammates, you haven't worked on a similar project. So there's going to be a fair amount of confusion, disorganization, and sometimes conflict at the start. Don't panic. That's normal. What you want to do is have open discussions, have some meetings. So this is actually harder this year. human beings build trust by looking at each other and spending time together. So whenever I was building a team in industry and I had to work with people, possibly from a faraway geography that I hadn't worked with before, I'd take them out to dinner. Okay, we would go out, we'd break bread together. You get to know these people, you get to trust them. It moves much faster. Now you can't do that, but what you can do is have some Zoom meetings because it's the next best thing. Rather than just saying, okay, we're going to send each other a couple of emails and we'll go off and do things and we'll hope it goes well. Spend some time even coding on Zoom together to get to know each other. And your goal is to kind of get through these relatively quickly, not panic when there are problems, but get into these higher levels of performance. Okay. All right. So you're there and you are trying to get to at least norming, maybe even beyond. And my strong advice there is spend some time looking at each other and talking to each other, even though you can only do it on Zoom. Because I'm going to end on this slide. We'll talk about this next week, but it would be useful if you go and read this article. So it's the New York Times article, which was Google's internal research on teams. Google set out to figure out what made some of their teams more productive and higher performing than others. And we'll talk about it. So I'm not going to talk about it right now. I'll end there. But read it, and then we'll have a discussion about this on Wednesday. It'll be, the reason we're talking about this is having some understanding of what makes stronger and weaker teams will help you in this course, and it helps you a lot in your career. Engineering is a team sport. If you ever want to move to a leadership position, so management or creating your own business or being a professor, you have to have an understanding of what makes effective teams and how you can help make teams effective. So a lot of that you learn by doing it, by working in a team, but it's also useful to read articles like this to get some insights into the research that others have done. So I'll leave off there, and we'll talk some more about this next week. I'll stay on the line in case there are any questions. Okay, so I'm going to pause the recording. Okay, so I see you have a couple questions. Are the speed exercises more lenient than the actual tests? So I think what you mean, exercise are the public tests, and then submit actually runs the same tests as exercise, first of all. So we rerun the public tests because part of your grade will be based on those. And then we also run some additional private tests. The private tests are no harder in terms of speed than the public ones. They are actually set exactly the same way. We have a reference solution that we've coded pretty well. We use the right data structures or the best data structures that we know of and so on. But as I said, we don't micro-tune it. And we give you 3 times that amount of time. So you can be 3 times slower and you'll pass the tests. We use that procedure for the public tests in EC 297 exercise. We use that exact same procedure for the private tests. So the private tests just call these APIs with essentially different street segments, different intersections, and so on. It's to make sure your code is robust against things like you haven't tried to hard code the answer to all the tests, because we just won't give you all the tests. So that's one reason. If you kind of were really sloppy in how you handle memory and only fixed the memory bugs that you saw made you crash on the public test, then you might hit a memory bug in the private ones. That shouldn't happen if you've been kind of careful in how you wrote your code. But we're trying to make sure people haven't overtuned to the public tests, with the most extreme example being trying to just hard code the answers. So, okay, so a question: are the IDs indices into a vector? So the IDs we give you, all of those IDXs, intersection index, street segment index, etc., are very nice indices into a vector. Okay, so you can make vectors with them because they go from 0 to some number. So that's on purpose. We create this nice ID space to give you the option of storing them in vectors, because vectors are a very fast and efficient data structure. So I hope that answers your question. So you can use them in a vector. And where you see, I could use these as indices into a vector, that's going to be your best solution, right? You generally can't beat a vector for speed if you can just directly access it with some index. There are going to be some cases where we're asking questions with strings and so on where it doesn't really make sense. And in Milestone 2, if you choose to use the OSM ID API or the OSM low-level API, that uses those huge 64-bit integers. Okay, those are integers, but they're enormous and you can't make a vector that big. But for Milestone 1, you're going to see the vast majority of the calls are asking for these indices and returning these indices, and those indices always start at 0 and go to some number, and that makes them very well suited to using vectors. Does that make sense? Should you be making hash tables? So hash tables are also a good data structure. They're unordered maps, as you know. They're a good structure for certain cases, and we'll talk some more about this in the tutorial next week. If you can do it with a vector, so you just have an index, so that goes from 0 to num street segments -1, you could use that index as the key for an unordered map, or you could use it as the index for a vector. Both will work. Both are order 1. The vector is faster. Okay, so generally, if you can do it with a vector index with an order 1 lookup, nothing will beat that. An unordered map will be within a constant factor, so it's not going to be terrible, but it's not going to be as good as a vector. Now, on the other hand, if you're trying to look things up by string, you can't use string as an index into a vector. You could search through the whole vector, seeing, is this string in index 0? Is this string in index 1? That's really slow. So in that case, an unordered map is going to be a much better choice. Hopefully that answers your question. So it depends on what data element is being passed in as your key or your index. If it's a nice small integer, it's kind of crying out for a vector, right? It's telling you this is great. So we guarantee things like street segment index. We have a function that is get num street segments. And we guarantee that every index between 0 and num street segments -1 is a valid ID. So we're guaranteeing that it is like a nice, dense ID space, which is a perfect map to a vector. Okay? And again, it's a hint. It's actually kind of demonstrating to you a technique by which you can organize data. This is one of the ways that you can actually make programs fast when they have a lot of data to move. If you give everything these nice integer IDs, because when we process the OSM data, it doesn't have these nice integer IDs. We make them all as we create the graph. And we do that so that lookups of the data can be very fast because we can store things in vectors. So it makes our building of the data that we give you more complicated, but that building we do offline. You don't care about that. Once we built it, you can use this nice, efficient method of storing things in vectors. In Milestone 1, you won't be able to do everything in vectors. So it should be kind of probably your first thought. Your first thing is you call the Streets database API and just see, is it fast enough, right? If I can just call functions from this API and answer it, that's great. If I can't, then you probably have to cache some data, like load some data in advance. If you can load that data into a vector, and the vector is of kind of reasonable size, like it hasn't turned into some crazy thing, you're not going to beat that. And if that doesn't make sense, you kind of evaluate, well, what other data structures could I use? And you will have to use some other data structures. This will not all be possible to do with vectors, because that's not the way the world works. There's a reason that you're taught these other data structures. They're quite useful. And obviously, from a pedagogical point of view, we would like you to learn one of the things we're trying to teach you in this course is, what is the value of different data structures? When should you use them? And you really learn that by doing. Right? We could go over on slides many, many times what are the pluses and minuses, but you really only understand that when you've made the choice yourself and explored it. Let's see. Were there any? I think I might have missed a question or so. Okay, so could I elaborate on how teams could write the code? Should we create different files for each function or work on the same file? Yeah, so I'll talk about that on Wednesday, give you some ideas for that. But that's a great question. What I would recommend is you divide up, who's going to write what function. So you should obviously have some meetings now and make a plan. And I'm going to set up the wiki sometime tonight, and you can write that plan down. And then making different files is actually a pretty good idea, because that you're not going to step on each other's code. because Git is good at merging changes as long as they're not to the same line, it'll actually work out reasonably well, even if you're working in the same file, as long as you're working on different functions that are in different parts of the file. But dividing it up into multiple pieces is even better, because it kind of by construction guarantees you're not going to step on each other's code and you've got good parallelism. So that's a great question. And then communicate, update your status of like what's working, what's not, check in things once they work, tell your team members to pull. So you're all kind of have a good view of what's going on in the whole project. You're not just each working in isolation, not getting code from each other, not updating each other on your status. So you're trying to do what's called continuous integration. Your continuous integration is that as you basically write code that works, you put it back in Git, so you commit it, you push it, and your teammates pull it, so that everybody's seeing, either the latest code or close to the latest code. There's not a phase at the end of the milestone where you try to put everything together, because usually what happens is you try to put everything together hoping it all goes well and something goes wrong. And that's very stressful. So you try to avoid that. But yeah, it's a great question, and we'll talk about it some more on Wednesday. Let's see. So have a good weekend, Ken. Are there any other questions? Let me open up the participants to see if there's anyone else on the line. Okay, looks like that might be the last question. So if that's the case, I'm gonna sign off and have a good Friday and a good weekend, everyone.